Well, hey guys, here we are at chapter 2. So let's go ahead and talk a little bit about what's going to happen in chapter 2. This whole chapter is the basics of the chemistry of life. And again, we're going to use the filter of trying to understand atoms and molecules, but applying it to biology and specifically anatomy and physiology. Some points to ponder or to think about as we go through chapter 2. How are living things organized from the atomic level up to the molecular level? What is pH and how we're going to use that with respect to living organisms. And then we'll hone in on the 4 basic macromolecules that are found in living organisms: carbohydrates, lipids, proteins, and nucleic acids. So let's start with just the building blocks from large to small. So matter is anything that has mass and takes up space. So if you can touch it, interact with it, breathe it, it is matter. Elements are the basic building blocks of matter. They cannot be broken down by a chemical means. I mean, you can break them down, but you get a nuclear explosion. So let's talk elements. There are several different kinds of elements. There are about 92 naturally occurring elements. An atom is just the generic for the smallest unit of any given element that retains the physical properties and chemical properties. We can take individual atoms and bond them together to form molecules. So if we look at the periodic table, this is a very small picture of the periodic table, but what you're seeing here is that we have arranged some of the different types of elements based on their chemical properties. If we look at column 1, what you're going to notice is all of these in column 1 share similar properties. And the reason is because everything in column 1 shares the property of having a single electron in its outermost shell. If you look at lithium, sodium, potassium, and then keep going down, because of this, all of them, when thrown into water, will blow up. Okay, not so much the hydrogen, but hydrogen's its own special thing. But it's spectacular, and they all share this property. If you look at everything in the last column, they all have a full outer shell, meaning they're very non-reactive. So things like helium, neon, argon. In fact, neon, we can put electricity through it, and all it will do is glow. We use that for like neon tubes. Things that you should know: the atomic symbol is the letter that's down here. Typically, it's still derived from its English name, but sometimes we run out of enough letters, and so then we have to use like its Latin name. So you can see sodium is abbreviated Na. The mass number is down here, and that is how much does it weigh on average. And then this is the atomic number, which will tell you how many protons the atom comes with. Protons are positive, and it also will tell you how many electrons it comes with, because protons and electrons are equal when they come before we actually react together. So here we can talk about the subatomic particles. Neutrons are neutral and uncharged. Protons are positively charged. Those two things are found in the nucleus. And then we have electrons, which are negatively charged and very tiny, and they are found orbiting the nucleus. So here you can see where those subatomic particles are. You'll notice that carbon, which has an atomic number of 6 and a mass number of about 12, we can see that it's the combination of neutrons and protons that gets up to the mass number of 12. It has the atomic number of 6 protons. It will also come with 6 electrons. Now, once it starts reacting, that might change, but that's how many it starts with. Here's nitrogen. You can see 7 protons, 7 neutrons. Its mass number is somewhere around 14, because that's the protons plus neutrons added together. These numbers are not always equal, but they're usually close. 7 protons means that it comes with 7 electrons orbiting in the outer shell. An isotope is an atom that has the same atomic number, because really the protons are what drive what that particular element is, but every once in a while you'll find that it has a slightly different number of neutrons. What this will do for us is help us be able to figure out what that average mass number is, and that's why that sometimes is different, just because of the different neutrons. Now, a radioisotope is an isotope that is slightly unstable. So it has a different number of neutrons, and it will kind of release some of these subatomic particles over time. And because of that, We know the concentration of, let's say, carbon-12 in the atmosphere and carbon-14 in the atmosphere. And as a living organism, we're consistently exchanging with our environment carbon. And so therefore, we have the same concentration of carbon-12 and 14 as it is in the environment. Once an organism stops living, that carbon-14 that's in there will start to decay. And we use that quantity to be able to date things. You can also use radioisotopes as markers inside organs. And sometimes we get so radioactive that it becomes radiation, which can be quite damaging. Here you can see where we've used a radioisotope. In this particular example, we have radioactive the radioisotope of iodine. Thyroid absorbs iodine, and then we can image that where the radioactive iodine is, and that helps us see if there's something wrong with the thyroid. We can also use it in using glucose molecules and some of that more radioactive, a radioisotope in glucose, and see where the brain is active, like in a PET scan. Molecules are made up of atoms that have been bonded together. They can be either made of the same atom or lots of different atoms. If we bond them together in a way that we steal electrons, this is called an ionic bond. It typically will cause one atom to become charged negatively and one positively, and then that is what bonds those two together. In a covalent bond, what you will find is atoms share electrons. If one is missing a couple of electrons and another has them, those electrons will then orbit both of those molecules or both of those atoms, and this leads to a covalent bond. So things like water would be covalently bonded together. Our next section will be about the property of water.